Hello everyone, how are you today? Today I want to teach you about how to make a silicon solar cell more efficient, okay? So the title of this presentation is going to be creating organic silicon junctions for improved solar energy generation. And let's get started, okay? So now let's first define what's organic and what's inorganic. Something that is organic contains carbon and at least some of this other element. Some examples are the coffee that you drink every morning and people around you because they need. The reason for that is because nature uses carbon as it calls it the building block of life, right? So we have bones, and that's our skeleton to get everything else, to put our hands, to define, to put our skull, everything. We need bones. So nature also has its own bones, and the bone is carbon, okay? And it needs at least some of this other element. Now, something inorganic is something like water or solar cells. They do not contain carbon. They can have anything else, just not carbon. Now, we have three types of solar cells. Speaking about solar cells, let's say, we have three types, okay? So we have silicon with an efficiency of about 28%, the ones you see everywhere. We have inorganic thin films with an efficiency of about 20%. Those are these ones, they are flexible. And we have organic solar cells with an efficiency of less than 10%. This contain carbon. All of these do not. Now, what's the problem? Well, silicon solar cells dominate the market right now. Shockley and Quasar, these two scientists calculated that only 33.7% is the limit for a perfect silicon solar cell. And the reason for that is shown here. So this is a silicon solar cell, and the sun is going to emit different colors, right? Different colors. Blue, green, yellow, red. Every color is going to have a different energy. Such as blue, for example, has a lot of energy. Green has a lot of energy. Yellow doesn't have that much energy. Red doesn't have that much energy. Silicon, absorbs all of them. Okay, but it doesn't need that much energy to create electricity. So it will take this too, but not. It will take also this too, but the extra energy that these two have will be emitted as heat. So the solar cell will just get hotter. So previous research added an organic thin film on top of silicon. It's called pentacene, the molecule they added. And they found that they can get it up to 41% efficient if they do this, okay? 41%. So from 33.7 to 41%. That's incredible. Now, I had a research experience for 2 months at the University of Texas in Austin. I was working with a professor, Dr. Sean Roberts, and he just assigned me a small project for my program. And this is what I'm doing. I put a molecule called naphthalene diamide on top of silicon. All right here, silicon, naphthalene diamide here. So naphthalene diamide will absorb the high energy while the low energy will not be absorbed, and it will just pass through to silicon. And that's how you can make a solar cell more efficient, a silicon solar cell more efficient, really. Now, what I really care about is what happens here at the interface. That is where they connect. Where they connect. Will the molecules be standing up like this, or be like this, or horizontal, or be like this, kind of vertical? That's what I care about, to see how the molecules look. Now, the way I do this is by putting silicon. This would be silicon. We have this chamber. This would be a method by vapor, right? So now we are going to add heat right here, right? And then we have the NDI right here, the vapor here, and then the substrate right here, and then we just add this, okay? And then with the ellipsometer, what happened is that um, so you see this camera right here? Okay, so this camera is going to shoot some light where this material will absorb, and what is not, it gets goes back to this camera on the other side, where it's going to estimate the thickness of the material that we were just talking about. Now, to see the orientation of our material, of our molecules, what happens is that we use this technique called grazing incidence, wide angle X-ray scattering. Really, we have a lot of techniques, but I use this one because it's the one that my mentor knew. Okay. Now, what happens is that we have the X-rays coming in this way, uh, hitting our sample, and then all the light is going to go to a detector in different ways. It's going to be scattered. Okay. And then we are going to see the surface of our film, the surface, with a microscope called atomic force microscope. Okay. Now, this is what the 2D image looks like. It looks a little bit uh, busy, but I will explain this right now. So first, let's look at this. This is a perfect stacking of NDI molecules. Okay, the distances between each other is 3.3 angstrom. That's unit of measurement we use. And now let's look at this, at the image. From here to here, that's 0 to 90. So that is just going to tell us the orientation of the molecule. So the orientation can be 0 right here, like this one's right here, 0, or it can be 90, like this, 90, right? So for example, from here to this point, from here to here is 25 degrees. So the molecule is going to be 25 degrees tilted. So from 0 to about 25, okay? And from here to here is going to be about it's going to be about 3.4 angstrom for this specific thing. But from here to here, it's just measuring the distances between them, okay? And I'm still understanding, trying to understand how this works, how to interpret this data. But all I know is that when we have a lot of this kind of circles, it's just light being scattered in a very specific place, like this, like this, like this, here, here, here. It just means that we have order crystals, okay? And we deposited the naphthalene diamide on top of a glass, okay, a piece of glass. Then so we got crystals, we got order. Now, when we see something like this, when we have a lot of rings, it just means that it's all disorder. It's all everywhere, okay? That's my understanding. And now, of course, this is the AFM image, the microscope image. All of these dots that you see right here, they're all pieces of crystals of naphthalene diamide. And then we can use that data and then put it into a graph. And then let's say we want to analyze this peak number 1. We can estimate the height. Here's the same image, but zoom. We can estimate the height. The height is about 2 nanometers, okay? So it's about the size of one molecule of NDI. Now, for really, what are the conclusions of this work? Well, we see crystalline order when of NDI when deposited in quartz, right, at high temperatures, right here, right? Quartz at 200 degrees Celsius, we see order, and we see disorder when we deposit NDI on silicon, in this case, methylated silicon, at 11 degrees and 21 degrees. So at low temperatures, we're going to see a lot of disorder. Okay, so what happened is really, in summary, I just want to tell you about something that we still don't know, but really substrate, the type of the surface that we use, that we place NDI on top of, will matter, such as whether we have glass or silicon, it will matter, and also the temperature. And now for future work, scientists still don't understand how this works. Don't understand how we can transfer charges to silicon. We know it happens, we still don't know how it happens. And then other people can study different types of NDI because we can modify the type of NDI we have, and that is also going to affect the efficiency. And finally, our work can help to understand or to really make a functioning solar cell. for all of you entrepreneurs. um, so now, what is my research experience in this project? Really, I found that researchers or master students, they're not really geniuses. They're just regular people. They just work under a lot of pressure. They have a lot of deadlines. They have to keep doing the experiments. um, they have to publish. They are under pressure because that's what they are for. That's the reason they are there, or they are here in the laboratory or at the university, is because they need to publish. That's what defines a scientist. A scientist who doesn't publish is just maybe like a person who is an entrepreneur but doesn't make any money or never starts a company, right? And now they also have a lot of group meetings. That's what we call it, group meetings, where all of us get together and then talk about what we have been doing or what we found or the problems that we had in the experiment setup, things like that. And then here is the principal investigator called the PI. In my case, it was Dr. Sean Roberts, the one who leads the experiment. He's the one who decides what big experiment we're gonna try to achieve, and then he is the one who hires people. In this case, graduate students or doctorate or postdoctorate or people like me, undergraduate, and all of us are working in to help him achieve his goal. Okay. And now in research, really, all of us are trying to dig a hole to find something new. Okay, or to try to understand something. But really, what we can do is we can turn around and look at other people what they're doing, and we can also learn from them, learn from what they're doing, and how they are doing, how they are digging their holes. Now, all of us, each of one of us, are studying a piece of a piece of a fly, every one of us. But at the end of the day, we learn to see the whole fly in places such as group meetings or by talking to people. Also, people get trained, graduate students get trained on equipment um, by appointments. So the university will give you an appointment for like, let's say, 1 hour, and then 1 hour, and then you have to learn the equipment that you're being trained on for in 1 hour. If you didn't learn, you have to go and probably ask somebody else. But that's how it works. And that is all I have for you. I really love you, and take care, okay?